Over the next 5 weeks, the world will be watching the biggest football tournament ever played. More teams, more matches, more moments than ever before. But almost no one will be watching what's actually behind the game. Except today, we are. The game of football, known here in the US as soccer, has been played for thousands of years. But the version the world is about to watch, it's faster, it's more precise, it's more engineered than ever before. For instance, balls used to absorb energy. Now they return it. Older balls used to absorb moisture. The newer, modern designs, they're engineered to resist it. Close calls used to rely on guesswork, and now they're backed by data captured in real time. And here's the thing, these aren't just observations. They're things that we've actually tested, measured, and validated using modern design analysis and simulation tools here at SOLIDWORKS. And today, we're gonna show you how. I'm Sean O'Neill, and welcome to SOLIDWORKS Live.
Every match has its defining moment. The shot that curves beyond reach, the split-second decision that changes everything, the goal that sparks celebration around the world. But behind those moments are forces you can't see. Aerodynamics, physics, data, and simulation. Today, we're pulling back the curtain on the science behind the beautiful game. This is the engineering of football.
All right, everyone, welcome to the episode. We're here as part of our first conversation along with Mike Sandy. What's going on, man?
What's up, man?
Oh, your
Good to
hands
see
are
you.
full. Yeah, absolutely. So we're going to be breaking this episode out into chunks, right? So we have a basic three-part structure. So we'll be talking firstly about some of the history of the great game of football. We'll be talking specifically in this part of it about the ground game. Then we had into a conversation about the airborne nature of football, right? We would love to get the balls off the air. And then also the tech that tends to be inside some of the more modern match balls. But firstly, thanks for joining, man. Appreciate
Thanks.
it.
Thanks for having me.
So before we get into the physics and the engineering behind the game, I wanted to maybe start with something simple, right? How much has the game of football itself changed over time?
Oh, that's pretty simple, but actually not that simple.
Nothing simple. I mean, nothing that's been going on for this long is ever simple.
Yeah, we started researching. It was really fun to dive in and research this type of stuff, learning all the way back about the China dynasties that used to play this, thousands of years ago. The Mayans played it. But the Europeans are the ones who really take credit to picking up the game and taking off all the way back to the medieval times, and became a little bit more structured in terms of like the mid to late 1800s is when it formalized as a game throughout Europe. So we got to give them credit for a lot of that action.
Yeah, wow, thousands of years. Like if you can trace a game back thousands of years, that puts you in very rare territory, right? A lot of changes, I'm sure, to rules, of course, to materials of the ball. We'll get into all that. But part of the premise of the episode, right, is to get a look behind the game, right? From an engineer's perspective. What's actually going on? What informs the game that many all around us know and love and are very excited to watch in tournament style very soon. So before we get into some of the studies and some of the results that we had, what were some questions that we were trying to answer through some of the simulation studies that we put together?
It's really funny you bring that up, because when we went into this, we had no idea.
You had no idea the questions.
I mean, I assumed things like the old balls of back in the 1800s probably weighed a lot more. I had no idea the material they were made out of. We learned pretty soon that it was leather, which made sense.
Like had you like held that ball before?
No, and no idea what the T model ball was or any of those things. As you can see, it has the shape of the T on there. That's why it gets the name. The internal structures, nothing. We just knew that they played with their feet and they kicked some sort of air-filled ball.
Yep.
But to go into the studies and starting to set up the simulation analysis, it really came down to like getting that first one up and running. Get the model geometry done, get in a sim, set it up, get the initial reaction results out of that. And then that's when we started to ask questions and do even more research. And it opened up a whole world of fun with our analysis that we were able to expose with simulation. So
I think probably a lot of our viewers, right, you guys saw the lead in, you saw that a lot of the studies that we'll be exploring in terms of their results and maybe not even so much the questions, but some of the answers and insights that we got from doing the studies, they regarded and directly contain the ball. So when we think about that question, like from an engineering perspective, how much of the modern game is actually tied in terms of how it plays and how it feels to the ball itself?
Yeah, it's actually a lot more than we initially thought of, but it's not because of necessarily the brand new ball, right? This leather ball going into a fresh match versus this modern day ball. It's what happens to the ball as you're playing it that affects it. You know, as we started to research like what makes a good ball design, it came down to kind of three main things: is like consistency of play. So you want to make sure that the ball is holding air. In fact, modern day balls are tested. They do a 72-hour test, they pressurize it, and they can't lose more than 20% of that initial pressure over time. These older balls didn't hold air. As they evolved, they tried to figure out different ways, you know, vulcanized rubber bladders. From Goodyear, Charles Goodyear was the inventor of vulcanized materials.
Wow.
They incorporated that. Didn't work out great, didn't feel great. So then they went to back
stuff,
to.
I gotta say, I love this kind of stuff though, because it's total just like fun fact territory where if you're going to like a pregame or like a watch party, these are like factoids.
Share these.
Yeah, so like make notes here.
The one I loved was they went back to a rubber bladder, but this is when we discovered that the biggest challenge that they had in manufacturing a good soccer ball was moisture. And this is where in our studies we learned like, oh, it makes a huge difference on a leather ball.
Like how did you even, like you mentioned, like maybe not so much going into it loaded with tons of questions and assumptions, and sometimes when you're doing design testing, you do have a lot of assumptions that you're looking to test, a lot of questions that you're looking to maybe optimize for. But what even led you down that path?
Yeah, just again figuring out like why did they change, historically why did they change away from leather? And there's a few factors inside of there, but the main one was the fact that leather absorbs moisture. And given it might not be a rainy day, but how many times have you gone out to your yard or to the pitch to play and you have condensation and there's moisture out there naturally?
Yeah, it's not always just like it's just soaked from torrential downpours.
Where does that water go? It goes into the ball.
It goes into the ball.
Soaks inside of this. And that's what we started to experiment with inside of simulation. So virtually we were able to take one ball, essentially. We had one material model set up for the synthetic panel. And then we were able to set up another one with a leather material. So different characteristics in terms of the modulus elasticity inside of it. Poisson's ratio is a little different. Density is different. Even though the masses of these balls are the same, that's never changed in the history of football, at least up to like the late 1800s. But as you play with this leather ball, it gets soaked. It gets wet, it waters down. And not only does it make it obviously really heavy and hard to play with, so like head injuries were a lot more common with headers.
I can't imagine.
Just overall fatigue during games. You have 90 minutes to play with a really heavy ball over time. But what we saw in the simulation results is that dramatically dampened the ball. So you're getting kicks that were less effective. You had to put a lot more power into a wet leather ball versus a ball like this, the modern day balls, which are synthetic. They're not prone to these water absorption problems that you get as they did back then. And this took them a long time, Sean. It was until like the 70s until the leather ball went away. So almost 100 years since the first original game started to pick up, we didn't see a synthetic ball evolve, partially because the material didn't exist. We didn't have the science back then. So in the 70s, they started to play with plastics, different types of polymers, and they were able to get to essentially that black and white, the 32 panel ball was the first waterproof ball, really making a big step away from the leather balls of the past.
We've come a long way, right?
Yeah.
When you think though about like from an engineering perspective, what makes a better ball? Like it's so easy to say, I just want the ball to be better, or this ball's better, right? But what does that really mean? Like what defines a better ball from an engineering perspective?
It really comes down to consistency over play, right? So again, I mentioned the air pressure being held. So the internal bladder, big deal there.
Yep.
That bladder has to not pop, break. Back in the World War II era, that's when they started to play around with different internal structural membranes around the bladder. So they would do like a cotton cloth, a material, and that helped give it a layer of protection. So you weren't going to lose or puncture the bladder. So consistency, that's a big one. Modern day balls have synthetic bladders inside of them or rubber bladders inside of them. They're well protected. And again, they have to go through that testing of 72 hours with no 20% pressure loss at max to be considered a viable ball for play. The other big thing is they want consistency and accuracy. And that's both on the ground and in air. And we'll talk a little bit more about the air flight in a little bit here, but On ground play, again, you have moisture, you have all of the different variables on the field that can change it. A ball from start to finish should be the same. In fact, we learned earlier today, really cool statistic about what kind of the overseeing body does to test the balls, but they'll fire the modern ball with a pneumatic cannon at around, 31 miles per hour,
Yeah.
50 kilometers per hour.
You said we were kind of researching it about at least 2,000 times.
2,000 times they cycle it, and it can have no visual impact to it. So again, these things got to hold up. They got to be really, really durable. They got to be consistent play. They got to be controlled no matter what the variables of the field are. And then the final one, which we'll talk more about in a bit, is the projection and the trajectory while they're in air. That has to be something that's controlled, right? They can't be chaotic by any means. And we'll learn about this ball didn't meet those requirements where the modern ball did. It just took them a long time to get there.
What about, I'm like squeezing the ball, kind of feeling it around, but like, stiffness, layering, material construction, like how much of that goes into it?
Yeah, it's a lot of it too, right? And if they make design changes to a ball, which they've done in this World match that we have coming up, you're going to see that in order for, again, they test it on bounce. So they'll drop it from a certain height. It has to rebound to about 130 centimeters from that height. Older balls or wet balls or sand beach balls, which we learned are different. Indoor soccer balls
Yeah,
are
I was
different.
amazed to learn that there were so many different types of balls that are used in different contexts.
It changes
even
that
through
density.
to today. Yeah, for different settings.
So they all have to sit within a requirement and have the equal amount of rebound to be allowed into an official match play ball. So inside of there, again, there's things like the bladder construction, the panel construction makes a big difference as well. You can't necessarily move from a 32 to a 4 panel without a lot of consideration in the engineering, the manufacturing, the design.
I'm smiling because we have a monitor over here so we can kind of see the feed. So I want to give a few shout outs. I see, yo, let's go. Ready for this deep dive. Awesome. Portugal champion. Which team are you cheering for at this year's big tournament? I see SOLIDWORKS asking that question.
Yeah, I always hear what the chat says about that. Who are you rooting for this year?
Well, we got someone saying Spain. Spain's right there. Super excited for this episode. Peter, we'll be calling you later. So make sure you answer your phone. Awesome.
Nice.
Keep the chat messages coming. We are watching them. We appreciate you watching, and we know you're as excited as we are to pregame the big tournament here. But we've been alluding to it here, right? We have two very different footballs from two very different generations. You're holding the older ball, right? So at this point, holding the older football there, what immediately, as opposed to say more modern, more engineered balls, like what immediately feels off to you about that ball?
I mean, you grab it right away and you'll notice the leather. I love the feel of it. It's nice.
It's a nice feeling, yeah.
It is, yeah.
Right.
You also start to feel that the panel construction isn't as smooth as the modern day balls are. You have a much stronger seam line through here. And then the big one is, to me, I saw this and I was like, it looks like an American football, is the lace stitching on side of this, which we will learn later on. This actually impacted some of our studies, which I never really would have thought it would have made that much of a difference. So the lace structure on it. What about you?
Well, yeah, it's interesting. Even how like pressurized the ball feels at different points, like around the seams, like that feels relatively inconsistent. And I suppose that kind of speaks to how remarkable like today's ball is in that sense. Sometimes just looking at an object from the past, I think everyone can relate to this in the chat, everyone viewing, looking at an object in the past, a different design iteration before, we tried, coats of paint, as a sort of artificial bladder or coating system, right?
Yeah.
You just gain a new appreciation for where you are technologically speaking. So yeah, the seams themselves and the amount of them.
Even the spherosity of it, right?
Yeah.
It doesn't, if you look at this, there's certain elements of this ball, and you probably can't see it on camera, where you're not getting a consistent roundness to it. And that's actually a standard required now in today's match balls, is they have to meet, do you remember what a plus or minus 0.2%?
I think it was 1.5%.
1.5%. Okay, that's a little better, but yeah.
But still, that's
really
that's
tight.
insane. That's super tight. Yeah.
So it's got to be really round, which makes complete sense.
Really round. So once again, thank you all for joining. We're talking, if you're just joining in, we're talking about the ground game here and some of the simulation studies and physics lessons that we've learned, and we're happy to share with you today. When we talk about, we talked about the older ball. It's on the ground. So you're basically saying this ball was absorbing a lot of moisture, like even in conditions where it wasn't, like there wasn't like a huge puddle. Like we've shown footage where we have, actual like puddles on the ground. It seems insane, like it's been raining for days. But even in cases where it's, again, there's like dew in the grass and that kind of thing, like it seemed to make a difference.
Yeah, there's gonna be moisture in the fields unless you're playing on pure dirt, or like sand for the most part. So they're gonna absorb water, and that changes the overall, characteristics of the ball. And we started off with this, looking at it in SolidWorks simulation in just the desktop version.
Yeah, I think we do have a clip for that. So you guys were running, I think, like a nonlinear
we did a drop test. Yeah, we wanted to see exactly how much that water started to affect.
So drop test across like multiple steps, right?
Yep.
Okay.
Yeah. So there's a nonlinear aspect of it, but there's a drop test type study, and it was the easiest way for us to consistently say, hey, let's just drop it from a given distance. We'll give it an initial velocity. We'll apply our custom material. In this case, we had the Trienda, which is a synthetic material. Once that was applied in the drop test analysis, this gave us a good benchmark to see, again, what are we learning about? What are we kind of investigating? What other questions might we have that we didn't know going into it? And we didn't have a lot of questions going into it. We just wanted to start to play around virtually with these balls to figure it out. Once we had the initial result done, they looked great. You always want to use your gut test. Does this look like I expect? And you're actually seeing a lot of the dissipation of the impact go through the wall of the ball. And this is a great graph. This is your velocity, response velocity of that ball. And in the synthetic ball, we had a great response to it, acted fairly rigid after that rebound happens. When we changed out the material, and that's as simple as just duplicating the study, swapping the material out and rerunning, is we started to see that this is the wet leather ball. That dramatically took away a lot of that response to it, and it dampened the kick, right? So you had to kick the ball harder with, this to be able to get the same reaction out of it, or essentially the same kick in this case, because we're consistent with the drop test. The same kick is not getting the same reaction of the ball. You're not going to get the same velocity. It's going to be slower. On top of that, it's just going to be harder to play with and more fatiguing over time because it adds weight to it as well. So inside of here, there was a couple things we looked at, like having internal pressure inside of the balls. We used shell elements in simulation to kind of speed up the runtime, and the nonlinear, the drop test analysis here worked great. But we had more questions, right? This started to open up a whole new area. Like, oh, we want to learn more. What about the flex?
It's interesting, yeah. It's like you go into it with not so many questions. You come out of it having many, many questions.
Yeah, exactly. And we need to answer more and more. And that's where we went to the 3D Experience platform. So this is going to be an abacus-based solver. It's the top in the industry for nonlinear solving. We have one of the best solvers out there that does more of a full product verification. So what I mean by that is, drop test to get that if-then. Well, what is the difference if we change the material? But now we have an idea of what we're looking for, getting into this explicit dynamic nonlinear solver that's got cloud compute to it, so we can throw tons of hardware resources at it that's not even in the same building to solve these. And this is where we lined up with an actual soccer cleat and started kicking these virtually to really get an idea, like down to the fraction of a millisecond, what was happening with the impact as the foot came through and kicked the ball, and to get some great comparisons of that. And yeah, it basically validated what we were expecting, was that a wet leather ball just doesn't play very well, and that is a major issue. You need a consistent ball throughout gameplay.
So I'm going to do a chat check-in here. Nice outfit. I need one of those SolidWorks soccer jerseys. New SolidWorks swag dropping soon. Hey, appreciate the compliment. There is a SolidWorks store, so maybe someday. That's a great idea.
Yeah.
Turkey champion.
All right.
Thank
you
you
got
guys
one for Turkey,
for joining. Some soccer ball
Argentina.
emojis. Argentina. Interesting subject. Thank you guys for jumping on. And again, if you have questions, feel free to ask them in the chat. But you mentioned a few times you didn't go in with a ton of questions. You had many more questions as you progressed throughout learning things based on the results of these various studies. What surprised you the most?
I think going into it, I was surprised to learn that the initial ball was round, same size, same weight. The only thing changed was just the material, and that the material changed from leather to synthetic was the same. That was like the most surprising thing, that kicking this in a dry condition is gonna feel the same as kicking a brand new synthetic ball. We'll learn that spinning it is different, right? So just a normal kick impact to it.
And then we're actually showing.
Yeah. Here's this is
the
the explicit dynamic solver that we did right on the cloud. So this is using cloud compute. You know, we had a soccer cleat here that we were just kicking the ball with it, and you can actually look at after the response of the kick, you're getting this vibration. It's actually the natural harmonic of the ball that's occurring as it goes out, and that will change as well depending on wet versus dry. And you can actually see the imprint of the cleat itself on the bottom view there. It's super cool.
That's super detailed.
Results, yeah. Yeah, it was really fun to get it up onto the Abacus solvers and start to analyze down to like a tiny fraction of a second to see what was happening with the ball, which is just super geeky and fun to do.
That's very cool. You know, before we go out, we talked about how a big focus of this conversation, as you guys have learned, is really the ground game, right? Through the history of football, right? We're going to get into some of the airborne elements of football. I wanted to ask, you know, if simulation, as you guys have found through the exploration of this project and its associated analyses, can have such an impact on something as seemingly simple and spherical as a football, how does that extend out to different pockets of industry and the applicability there?
Yeah, I mean, obviously we know that back in the 1900s, they didn't have Abacus solvers on cloud compute to help solve.
I don't think I have to Google that.
A lot of these challenges. So the iterative process to get, you know, from that initial leather ball to today's modern ball took a long time because it was physically building a ball, testing the ball, iterating through feedback and those cycles. And today we still do that. And a lot of companies out there that don't incorporate simulation or do it very little in their product development still go to a physical prototype, which you always want to do.
Yeah, you're not like completely eliminating that.
Never,
that's
right?
cool.
That's always going to happen, be part of the design process. But your expectations of success are going to be much higher when you're integrating simulation very early in the process and throughout. So again, using SOLIDWORKS simulation built right inside of our suite of CAD design products, you can do those quick iterations right up front, the if-thens, ask a lot of questions, learn, figure out, we have a ton more questions to ask, you know, bring it into a full product validation suite like we have with the Abacus solvers on the platform. And then when you go to that final physical prototype to test it, your likelihood of success of coming out with a ready to go to market product, whether it's a ball or a massive machine, way better, right? You're gonna bring down the design cycle time, get to market a lot faster, and have a lot of fun investigating along the way. So what is going on?
I'm massively distracted. I'm sorry, but we have like an actual soccer player here. But before we get there, we have like 2 questions I want to get to. Thank you guys for sending them in the chat. I appreciate it. If we can just scroll up just a little bit. Do you think it will be a big difference using a different type of football boot? That's an interesting question.
We talked about it with, like, I don't know if you guys remember when the Predator, I want to say the manufacturer, came out with the cleats on the side, and I think we'll learn maybe a little bit more about that. But yeah, the cleats make a difference. I asked our rock star when we originally shot the video whether or not he uses like a carbon sole, and he said he hasn't really seen much difference in terms of the cleats he uses. But it would be something, again, we'd love to investigate. Simulation would be a great way to do that, is to look at if-then scenarios of like carbon-soled cleats versus carbon insoled line cleats versus a standard, you know, plastic type of cleat and so on.
So there's a question: can SOLIDWORKS simulate the dynamic motion of a knuckleball shot like the famous free kicks? Do you want to maybe save that?
Yeah,
Because I think we have just got to answer that question in just a bit. Do you want to head over there?
Yeah,
cool.
I want to see what's going on.
All right, yeah, follow us. We're going to introduce you to Ronit here.
What's up, Ronit?
Ronit.
Hey, what's up, guys?
What have you been doing, man?
Woohoo!
Oh, look at that.
Let's go.
Look at it.
Sean, what a pleasure.
What's going on, man? So, man, you're working up a sweat out here.
I know, man. It's been a long time, so I was just saying if I still have the skills or not. And I'm struggling, yes.
That was almost a goal.
Awesome. Mike, good to see you.
I think everyone got a sense of this, but you played a good bit of soccer in your life, right?
Oh, yeah, man. Definitely was a soccer player back in high school, back in college soccer. So quite a lot of years under it, but then this is a long time ago. So the joints and hips and everything are super tight.
Yeah.
Oh yeah, and the cardio, of course. I'm like sweating after like juggling the ball for 2 minutes. So yeah.
It's never good when someone, I'm sure all of you can relate in the chat, it's never good when someone complains about no longer being able to do a certain thing at a certain level, and you're just like, I'd never be able to do anything approaching what you can do now.
Yeah.
Like, do you realize that?
Yes, that thought happens.
Your baseline is still better than my best.
Yeah, the 20s bicycle kicks, yes. 40s, nah.
So, Ronit, there was a question in the chat that we read off as we were walking over. The question loosely was, can SOLIDWORKS flow simulation simulate the sort of flow of a knuckling ball?
We can simulate a lot of things that will actually predict when the ball is knuckling or not, absolutely.
We're going to talk about that.
Yes,
That's
yes,
one of
we're
our
going to
planned
talk about
topics,
that.
too.
We're going to talk about the physics behind it and all that lovely stuff.
Yeah, and some of the more of the history of football to give you more factoids for your pregame parties.
Right.
But you probably heard we were just talking about the ground game. We're getting into the airborne game here, which you were giving me some lessons here at the Bancroft Field. So first question, before we get into simulation and all that, looking at results, when you are looking to hit the bending shot like we saw, in the thumbnail and the teaser for the episode, what are you actually trying to do with your body? Like, how are you trying to approach the ball? What are you trying to do with your legs?
Sure.
All that.
Yeah, great question, Sean. So it goes back to the basics of soccer. Every time we had a coach, this is one of the first things that teach you is your run-up, where you plant the foot. It can't be too back, can't be too forward, right next to it. And then how you contact the ball, the contact point on the ball, the contact point on the foot, how your foot wraps around the ball, and then also the follow through. So these 4 or 5 points, when you work on them, and of course you practice quite a bit, and becomes one fluid motion, that's when you can generate that curve, which is basically generating a spin, and in other effects, it's starting the Magnus effect. So kicking motion generates the spin generates the pressure difference, activates the Magnus effects, and you see the ball curve.
Magnus effects.
The Magnus effect.
Keep it in our pocket for now.
Yeah.
Once we get to the physics, because we got a lot to talk about there, right?
Yep.
But when you make contact, because I've related to you guys. When you shoot a jump shot, you're playing basketball, right? You kind of have a good idea if it's going to go in if you've played enough.
Yeah.
If you hit a baseball, right? You have a good idea if you've made sufficient contact to maybe get a base hit, maybe get a home run. You kind of know right at that point of contact. In this sense, I haven't played a lot of football. Do you have a good sense of whether you're going to hit the desired kick, in this case maybe a bending shot, right at that moment of contact, if you're familiar enough with the game?
Yes, Sean, it's very, very cool question, to be honest. And of course, if someone who's had thousands and thousands of hours of practice, like curling and knowing what it feels like, and the 4 or 5 points that I mentioned, the placement, the contact, the follow through, when all of them you do it perfectly, and also you hear the the audio contact with the ball, there's something about that, everything coming into cohesion, that you as a player, you do feel like, okay, I did everything perfectly, this would be a great shot. And now, in addition to that, if the wind and the airflow is working in your on your side, then you know that this ball is curving, going away and to the top corner and stuff. And to be honest, in my whole career, I've done this actually once, perfect curl shot, top corner, before even it's... Yes, it was that good. It happened once, and I still remember. And before it even hits the net, I'm like already celebrating with my friends. Every time I see this in professional soccer too, I think it's cool. Very risky though, because if it doesn't go in, you look not fun.
So I'm just checking in on the chat here on the iPad. Oh, interesting. We'll talk about this. So some people actually saying, amazing simulation, nice, very interesting, supporting Mexico team. All right, so answering your question from earlier, Sandy, who do you want to win? Definitely think lace location on the cleat can make a difference.
Yeah, sure,
definitely.
Makes sense. Yeah, for sure.
All right, let's see. Thank you guys for the questions, the comments, the shows of support for your favorite teams. Keep them coming. We'll keep checking for you here. All right, so getting back to the flow here, let's talk physics. Let's get back into it. So from a physics perspective, you teased us a little bit earlier talking about the Magnus effect, but from a physics perspective, I watch soccer and I see a ball curving through the air. Just seems like it's magic. Yeah. Right. But from a physics perspective, what is actually happening to that ball?
Yes. So let me see the balls, Mike. So it's actually magic. It is magic what's happening, but magic has like different terms. Like sometimes magic is called physics, sometimes magic is called chemistry, right? So it's magic. Yeah, so what's actually happening, guys, when you kick the ball and it's curving through air, through a medium, in this case will be the air, you've got the ball spinning and you've got the air hitting on one direction. So you've got one side of the football that's accelerating the air, and the other side of the football where it's decelerating the air because it's going against the flow of the wind. So what's happening with the side that's accelerating, we're creating a low pressure system over there. And on the opposite side is a high pressure system. Of course, this is Bernoulli's principle 101. So with this pressure difference, what happens is there's a lateral force that gets applied to the off axis of the football, and that's what actually dictating where the ball is going. So magically, actually, it's air that's physically pushing the ball based on how the spin is happening. So 3 things to keep in mind over here is the spin, of course, the Magnus effect, and of course, the velocity that you kind of kick it from. And these are the variables, guys, that we actually input into SOLIDWORKS Flow Simulation, and it quantifies what you feel as a player, what you feel on the simulation, so you can kind of validate these things. And to be honest, as a player, these are invaluable information to me to become a better player. How do I want to curve? Where should I aim the ball to curve a little bit more? So things like that. Yeah.
You guys are saying in terms of different lines to remember, right? It's like low pressure, high velocity.
Yeah.
High pressure, low velocity.
Yeah. So
right?
High pressure, low velocity, low pressure, high velocity. That's that's Bernoulli's principle, and it's literally one of the first things we start learning about when it comes to airflow.
The Magnus effect comes down to the rotation, right?
Right.
Because Bernoulli's will also is the dividing or driving principle behind the airflow of like a wing.
Yeah.
And, how does an airplane fly? But where the Magnus effect comes in is that we get that same principle based on rotation.
Rotation. Yeah.
It's cool.
So one thing that I think surprised me overall as I started to digest some of the study results that you guys had obtained through this project is that older balls, right, they used to perform less predictably in flight. And we spent a lot of time just a moment ago talking about how, and everyone can see and everyone knew heading into this episode, right, the ball is a ball, it's a sphere. So you might look at that and think how different could it be? And if it did behave less predictably in flight, why would that possibly be? What was going on with these older balls?
Yeah, I can start on this one because
take away.
Ron had set up the studies. Basically, rotating mesh was how we set up that rotation region to it. Once we got it in there, we did it for all the balls. We had the 2 balls, this one here, the old ball and the new ball. Refined really nice mesh around all of the little grooves and anything that could affect the flow path to it. And on the old ball right here, you'll see it, we actually get this vortex shedding. So vortex shedding was happening based on the laces. So if you have a kind of a tangential direction of that lace swinging around during rotation, and that was causing a massive distribution change or a fluctuation in that pressure. That lateral force is what we're looking at actually here, not the pressure, but the lateral force based on the pressure differential, causing it to be less consistent versus seeing it with the standard ball. So yeah, having these laces on the edge as it's rotating, that was interrupting the flow enough to dramatically change that lateral force. Or because we don't have laces, it's a much smoother surface. There's still texture to it, there's still grooves in this ball, but they're consistent all the way around. So you're gonna get much more consistent lateral force and a much more consistent arc when you're with the newer ball design.
Oh yeah, 100%. Mike covers it. And one thing to notice on the old ball, along with the laces, it's a very inconsistent ball. It's not very spherical, like Mike mentioned in the previous, structural bit, where if it gets wet, it gets heavy. So it's a very inconsistent ball. And when you have an inconsistent ball, you can't reliably, predict the flight path or control it enough where you want to hit it in the top corner. So it becomes incredibly hard. Whereas the newer balls have a more predictable sort of surface, because the non-uniform surface on that ball creates this very erratic sort of a boundary layer, turbulent boundary layer on the surface, which makes it hard for us to predict it. And on the opposite side, a lot more predictable on the new ones. Yeah.
Just checking in on the chat here. So let's see. How did the balance of the ball vary throughout the years, and how did it impact the game? Interesting. So were we able to glean some of that through drop tests in terms of the bouncing? So basically the question is, how did it impact the game? And you may even be, I'm sure you'd be able to attest as well, just at a player level, like a football player level, just different balls.
So I would say in the modern history, the balls, except for the 1 year, have been fairly consistent. Of course, the engineers towards the bounce, like the modern balls, because before this, like the old balls made out of leather, or the different types of the rubber inside it, vulcanized rubber that Mike was talking about, they all have different material properties. They're all going to interact differently when it comes to contact or any nonlinearity that happens to it. So over the years, as the product became better, as the materials became better, and now we've got synthetic materials that are thermally bonded, it's of course going to be a little better. So right now, if I bounce it, it has a lot more return back, a lot more push back, whereas the older ones, if you bounce it, it might not have that much kind of a bounce. It might stay damp.
Yeah, the biggest one we saw history speaking wise was 1839. Charles Goodyear came out with vulcanized rubber. And again, they wanted to figure out ways to handle the moisture situation. So vulcanized rubber bladder was brought in versus they were using a pig's bladder before to fill it up, which is weird. But hey, use the tools you have, right?
So.
So the vulcanized rubber was a really nice way to have a synthetic variation or a rubber variation inside of the ball, but it affected the bounce. It was much more dense. It didn't respond as quickly. So back in, I think that lasted till 1862. 1862, they went to just a standard rubber bladder, and that's what we've had ever since. So like over 130 years, same bladder technology. They've just changed the outside material quite a bit. But again, looking at the structural results that we had, is we found that the leather actually responded very similar to the synthetic ball under very similar conditions. It was just when it got wet, we had a big change in the response. So to answer that question.
There's a question in the chat that we brought up. We said we'd get to it, right, about knuckling. We asked it from a flow simulation perspective, but there actually are, and you were speaking with me about this, historical examples where the knuckling of the ball was not predicted and it was not preferred. So this was the 2010, I believe, tournament. So talk to me about what happened there. We've been talking a lot about like materials and different compositions of different match balls. And so relative to the ball that you're holding, Sandy, right? That's a much older ball. 2010, you figure it's more modern, it's more engineered, certainly relative to what we had in the past. So how did that happen? Like you were seeing a lot of knuckling and it just wasn't, at least as a viewer, maybe it wasn't preferred, wasn't a good experience.
Oh, as a viewer, it was a great experience because it was just all over the place. But yeah, I do. So, but as a player and as a keeper, as players, it was actually a very tough ball to play with, tough to control. So, what was actually happening, Sean? So, the company that designed the ball, the goal was to actually make the ball better, to make the ball more smooth, more round, and just perfect in all ways. And on paper, it looked amazing, So. But what in fact had happened is the ball was made way too smooth. It was way too smooth. So they went from a 32 panel to an 8 panel thermally bonded ball. And when you go from a 32 panel to an 8 panel, you are using a lot less of the seam. The total seam length and the grooves, they were a lot less. And seams are very important when it comes to aerodynamics. So with less of those seams, now imagine if you kick the ball with less seams and it doesn't have any spin and it's flying through the medium, which is air. So you have these asymmetrical channels on this ball. So basically the air was streaming asymmetrically through those channels, which made it incredibly hard for players and keepers to predict. Now, the problem was that this was happening at a very high speed. So we're talking like 50 miles an hour. So imagine if you're a keeper and 50 miles an hour ball coming to you, 5-0. So rips, like really, really high rips. And at that speed, because the ultra smooth boundary layer around the ball, it could not decide whether it wanted to stay smooth or laminar, or if it wanted to go turbulent. So you would be predicting something and the ball is like dipping and swerving and it's just all over the place. Fun to watch, not really fun for the keeper, and like I said, not really fun for the striker to control as well. And they fixed it, in the next tournament. I think it was the Brazuca ball, where they added more irregularities on the outside, which made the flight path and the knuckling effect a little bit less, so a little bit more predictable flight path. So this is a great example, great case study.
Actually.
Yes, so that's a great point you brought. So NASA actually did a case study on this, and they figured out, the critical Reynolds number zone for that particular model was quite high. So that's kind of like the specific range where the airflow around becomes erratic. You can't really predict it, and NASA predicted it because it was too smooth. So added those blemishes on the next model, and they were able to control the ball quite a bit.
All right, so just checking in on the chat here. Thank you all once again for sending your messages and just being excited about what we're showing here. So what's the question here? Can we simulate different surface finishes on the ball to know which would be best with more or less twist when it's been kicked?
I mean, if you have the CAD model of whatever seams and surface, yeah, you can go deep and you can really create some really cool meshing around the balls. The finer you go, the more accurate you get. So it's all a matter of do you have the right CAD model and the right boundary conditions, basically. And yeah, we can simulate that.
Yeah, I mean, the concept behind flow simulation is to discretize the volume around the ball, that air flows in there. And we do that with tiny little cubes. So the smaller the cube we can get and fit in to match the geometry and the surface finish itself, tiny little cubes, we can calculate what the air going in, the flow is going in, flow going out, how it changes through that. And that calculates the next cube, the next cube, the next cube, and that builds the overall model. So for this one, when we set up the simulation, we wanted to make sure we had a lot of representation of those little volumes around the lace. And same thing, all the little channels that are in this ball, all the seams.
So basically, like these are like the areas of importance.
Yep. Yeah, we had just high refinement of the tiny little volumes there to be able to calculate out what the airflow is doing and then extract out our global results out of that. So,
Sean, another thing to kind of mention over there with the reason why we want to do that, and with this disaster that happened in one of those years, is why you want a full product verification of your model before sending it out to be used in real world. So this is where the Abacus platform, the full product verification comes very handy, because there's a lot of things happening over here, and we want to be able to analyze each and every one of those before shipping the product out.
So we've been talking a lot about the history of football, different conditions, different types of match balls. One thing I want to ask you that is very specific, you guys, to the simulation domain as it relates to airflow around the ball and what you learned there. When you think about a casual viewer, casual fan, what's one of the things that you saw in the simulation results that the casual viewer, the casual fan, maybe someone who isn't so engineering minded, might never notice?
Yeah. So this is a very funny question, Sean, and I love this question, because now, being in simulation and being in sports, like, I see the world differently. I see streamlines, and if I'm catching a plane, I'm seeing streamlines over the wing. So I'm seeing colors. I don't know if it's a good thing or a bad thing, but I'm seeing colors, guys. So even when we were on this project, when we were working on this project, we started with your very initial pressure drops, which made me think, okay, you've got spectators, you've got players that are playing. They can see the ball move and rotate and spin and knuckle, but they don't really see what's happening with the air around it. And now I can visualize streamlines and vortices and wakes that a comet leaves behind the ball like a comet. I can visually see those in different color gradients and orientations and stuff. Yeah, that's pretty cool. So now when I'm kicking the ball, I'm like, ooh, there's a streamline that's going that way. Okay, so that's one. There are many results you can pop out of running a flow simulation on a product, and the stagnation points. It's good to see where the air hits the front of the football, and then basically there's no velocity of air here, but then you also see the spin and the shifting of the axis and the Magnus effect. I don't know, man. I can talk about this all day, every day. This is so cool.
We can quantify all that too, So we see it, you obviously get an understanding, and visualizing it helps, because you can't really make something better unless you can see why it's not a good product in the first place. So the visualization aspect's great, but then the quantification side of it too. Like, we looked at surface parameters on that ball, and we were able to actually look at the tangential force equating on that one versus this one to see, that's why that ball is going to hook a lot harder than this ball, just based on that geometry of the laces and what that would cause to the airflow as it's rotating. So for me, to answer your question, Sean, it was just like, holy cow, any minor detail that's not symmetric is going to make a major impact to the play of the ball. I thought that was really awesome.
Yeah. Well, one thing, Sean, it's funny when I was on this project and, being in simulation for all these number of years, it's funny to understand, like, how we can view things differently, how we can, make our products do, a lot better. And it's, without these tools, without full simulation, the variables that we input, it'll be really hard to make a product that's quite good, or it'll take a lot of time and a lot of prototypes and stuff. And as a player, it was, working on this project that was really fun for me. As a player, I feel the physics and everything on inside. So I'm talking to myself in a language as a sports person, but then when I jump onto the simulation, I'm talking the same language in physics. So instinctively, what I'm feeling, I can quantify that. And that was a very cool feeling. Okay, I know what's happening.
Yeah, that's cool.
Very neat. Well, it's cool to hear that, the ways that you've interpreted results, especially, with him being a player, right? For many years of your life, have actually informed how you feel the game, right? That is such a cool concept. I also want to say you are actually a very good coach of the game. Like, I have not played much football in my life. I just have veered to other sports, other activities, and you got me like kicking straight, like curving the ball as well. So if you guys want to, we're at a soccer field. You guys should go practice your favorite bending shot.
I've been waiting for you to ask.
Yeah, I do. We do have to make a video call, myself and the audience. So yeah, you guys go ahead. Okay, so this video call that I'm talking about. So we've spoken about the ground game, the airborne game, but what we really haven't spoken much about, going almost chronologically here, is the tech inside of the modern match ball today. And antennas and how it interacts with the elements and devices like these. So let's give it a go. Let's give a call to our physics friend Peter, and let's talk all about the tech inside the modern match ball. Stay tuned. Okay, so let's see if we can connect with Peter here. Now, before I call him, let's imagine together, in our mind's eyes, a moment that every football fan has seen before. It's late in the match, the shot hits the crossbar, boom, drops straight down. And everyone immediately asks the same question, right? Did it cross the line? So for most of football history, moments like that depended entirely on human judgment. A question that I'm hoping to answer for us practically here with Peter is why and how has the sport eventually moved towards tech-assisted decisions? Today, these aren't just footballs anymore. There's actually technology inside modern match balls and beyond helping to determine what happens in more of an objective sense in real time. All right, look, I think we're ready now. Let's phone a physics friend to learn more. Okay, hopefully he answers. It'd be really embarrassing if he didn't. Oh, Peter, hey. Hopefully we're coming through clearly from the stadium here.
Hey, Sean. Yeah, I hear you loud and clear. And thanks for having me on the show today. It's actually kind of perfect with you there in the stadium talking wirelessly to me here in my office about wireless technology inside a soccer ball. It's a perfect venue for this conversation. And I'm really excited to be here because this project really sits at the intersection of engineering and sports and simulation and electromagnetics all combined into one.
What I find fascinating is that we are literally standing here inside of a stadium making a live wireless video call. Couldn't have done that, say 10 to 15 years ago. But if this were a real game today with tons of attendees, we might have modern match balls that are also communicating data wirelessly during play, right? So first off, how are moments like these, did the ball cross the line, actually determined today? And what about things like offside rulings and those sorts of common but crucial football calls?
So historically, things like offside calls and goal line decisions were made entirely by the referee and assistant referee. And in a fast-moving sport like soccer, that's incredibly difficult. You've got the ball traveling over 100 kilometers an hour, you've got players all over the place blocking the view, bad angles, and the difference between a goal and no goal can be a couple of centimeters. So modern systems developed to help take the ambiguity out of these decisions. Now, starting with the goal line, you've got high-speed optical trackers monitoring both goal lines. So we're talking multiple cameras pointed at each goal line so we can exactly determine where that ball was and whether it crossed the line. And now for offside calls, we have a smart match ball. That means we have sensors and electronics embedded inside the soccer ball. And what it's actually doing, there's an inertial measurement unit in there. And that actually measures the acceleration, the spin, anytime the ball is even slightly touched or bumped. And that lets us figure out exactly when the ball was touched for offside decisions. So today it's really a combination. You've got high-speed camera systems for the goal line decisions, and then the smart ball to help with offside decisions.
Okay, so to intersperse a bit of soccer history here, how did we get here? When did it become apparent, in other words, that reliance on referees and replay simply wouldn't always cut it?
I think it was really the accumulation of controversial moments over the decades. And soccer's always had these big, was it a goal or not moments. And because the sport is so low scoring, one bad call can change the outcome of a game or even an entire tournament. And replay helped, but replay still depends on camera angles, visibility, frame rate, etc. There can still be some ambiguity and bad angles and essentially not being able to make a decisive call with video. And I think that's why the sport and sports in general are moving towards more objective measurement systems rather than subjective calls. And that's really what's driving all of this, is rather than make a subjective decision about what we think happened, we can measure the data and decisively say what really happened.
Okay, so let's get into the modern in-ball technology today, Peter. How fast is the ball tracking data actually being captured during a match?
Well, that's a great question, Sean. And to answer it, really fast. Modern inertial measurement units, or IMUs, inside the balls can operate at up to 500 hertz. That's 500 times a second that data is being captured. Now, why do you have to measure the ball's acceleration data that frequently? Well, the higher the frequency you get, the more often you sample that data, the more resolution you get, and the more accurately you can answer the question, when exactly was that ball touched? So the faster the measurements, the more resolution. That's basically it, and it's done 500 times a second. But it's not just the speed of the measurement. That has to then be transmitted from the ball to a receiver and from the receivers to the officiants that are actually going to make the call. So it's not just the high speed, it's also having very low latency communication as well.
You know, one thing I think most people never consider is that in a packed stadium, you've got tens of thousands of phones, wireless devices, cameras, just signals everywhere. So how difficult is it to maintain reliable communication and tracking accuracy in an environment like that?
Stadiums on game day are electromagnetic chaos. You've got tens of thousands of phones, you've got Wi-Fi devices, Bluetooth devices, production broadcast equipment, etc. It makes it a really, really messy RF environment. And then you have the stadium itself. All of that concrete and steel causes reflections and what we call multipath effects, where signals can bounce around and interfere with each other. And that's why simulation is so crucially important here. We can take all of these things into account. We can, to start with, take the ball and measure how the ball's material actually affects the antenna signal. Then we can look at the entire stadium. We can see how that signal propagates through the stadium, look at reflections and dead spots, even test orientation of the ball, and ensure the reliability of the communication in a realistic environment.
Okay, so from your perspective, what impresses you most about the fact that these systems actually tend to work consistently in real time under live match conditions?
That's a tough question because there's a lot of things that impress me about this system. But if I had to narrow it down, I would say probably the combination of miniaturization and ruggedness of this system. I mean, it's a pretty impressive feat to be able to take a sensor, battery, and antenna package and shrink it down into something small enough and light enough to be put inside a soccer ball and be used in gameplay. But it's a whole other thing to then have that be kicked around by elite athletes for its entire service life. Like, think about the impact of one of these pro soccer players kicking a ball that's going to launch it at over 100 kilometers an hour, and then think that happens over and over and over again. Well, this system still has to accurately capture all of that data 500 times a second and transmit it out to a receiver. So the fact it can be that small and take that much abuse, I think, is really, really impressive.
So how did you model a simulation of lifelike game and stadium conditions? And overall, what surprised you about the results you saw?
Well, that was the most interesting part of this project, and also most of the work. Moving past the antenna itself and looking at its installed performance in its environment. And the reason for this is antennas are tricky. You can design a beautifully performing, excellent antenna that works in free space and tests very well in a lab. But as soon as you put that next to anything, if you mount it in a soccer ball or on a car or literally put it close to anything else, its performance will drastically change. And that's what we need to consider here. So it starts with accurate geometry. We actually modeled the entire ball in SOLIDWORKS and the rubber bladder and the pocket for the antenna and the antenna itself. And we were able to look at, once we have the desired antenna performance, we can see how that's affected by those ball materials that are put around it. And by accurately capturing the close environment to the antenna, we can actually accurately capture its performance. And then by moving beyond that, we look at the stadium itself. And again, using a SOLIDWORKS model of an entire stadium and applying accurate electromagnetic material properties to that, we can look at how that signal propagates out from the antenna through the ball and into the stadium, how it bounces off certain features, where it reflects, where you get dead spots. Some orientations of the ball will have stronger signal than other orientations, etc. So it's being able to capture all of that. And it comes down to understanding what that environment is and trying to get your simulation to reflect it as closely as possible.
Okay, so beyond football, how are these electromagnetic simulation tools being used to test realistic conditions and solve everyday problems in the rest of the real world?
I think that's a really powerful takeaway from this whole project. People may see a soccer ball and an antenna and think this is some niche sports technology story, but it's really not. The same principles here, having an electronic system installed inside a real world product, that happens every day, all the time in the world around us. And I mean, let's look at automobiles. In an automobile, you have Bluetooth, GPS, cellular, keyless entry, autonomous driving systems, etc. Aircraft, you've got complex radar and communication systems and electronics. Medical devices are driven by electronics and wireless communication, and even household devices and household appliances are becoming connected smart devices now. The challenge that we face today faces product designers and engineers around us every single day in just about every product category. And the challenge is the same. It is, how do you predict the performance of an antenna installed in a real product operating in messy real world operating conditions? And that's not limited to soccer. That is literally every industry out there right now. And electromagnetics used to be a bit of almost a niche topic, but it's not. As wireless systems are now integrated into just about every product category, this is not something as mechanical engineers that we can ignore anymore. This is now mainstream, and we have to deal with it. And simulation is a great way to deal with it by being able to test these systems virtually. Rather than building a bunch of expensive prototypes, you can build it virtually, make good design decisions early, validate those decisions, and basically have high confidence that your product is going to work the first time. So that's my biggest takeaway, is that this can be transferred to just about any product out there.
All right, Peter, Listen, I have to go before the parking lot gets way too hectic out there. Thank you so much for your expertise, and we'll talk soon. Thank you all for learning along with us here today. Hey, if you're interested to learn more about what you saw today, you can visit our website where we have 3 separate videos exploring the analyses we conducted across the evolution of football. And if you're interested in exploring some of the analysis tools used in these fascinating studies, you can always contact your SOLIDWORKS reseller partner to learn more about the specific problems that they can help you with. And speaking of learning and investigation, did you know that we recently launched a white-hot SOLIDWORKS tutorial channel? One of the biggest search queries out there on YouTube as it pertains to SOLIDWORKS is how to learn it. And if you've been using SOLIDWORKS Design or SOLIDWORKS Simulation for more than, a couple days, you know that that can be a tall ask. So we've made it easier by providing catered training and tutorial experiences in a dedicated space for your viewing pleasure. Whether you're an industry user, a student, or a maker just getting started, we assuredly have something that can help you there. Okay. Look, I told Peter I'd be heading out shortly to beat traffic, and I'm going to do that. But in the meantime, subscribe to the channel, hit the notification bell, and we'll see you shortly on the next SOLIDWORKS live stream. Enjoy the rest of the tournament.
Want to learn SOLIDWORKS fast? Whether you're just getting started or leveling up your skills, this is the official home for SOLIDWORKS tutorials, designed to help you build real skills, solve real problems, and work more efficiently. From sketching and assemblies to drawings and advanced techniques, we break it down step by step. Then see how it's used in real-world design over on our official SOLIDWORKS channel. Subscribe to SOLIDWORKS tutorials and start learning SOLIDWORKS today.